Hello, good morning, everybody. Here we have Tara ma'am, our head of department, who will be addressing LSAD. And yes, ma'am, over to you.
Thank you, Arafat, and thank you, Stephen. It is wonderful to see all of you. I think we have 40 students almost. Yes, Arafat? Hello?
Yes, ma'am. We have around
Yes,
47
Arafat.
students.
Wonderful. That's a very good number. And I think all of us are really excited to meet Stephen here. Stephen, before I begin, I'll just give you a little introduction about my university and our school. Our school is actually a part of a university, which is a lovely professional university. The university started from a humble 1.5 acres and now is a whooping 1,200-acre campus. It houses almost 45,000 students on campus, 5,500 faculty teach here, and we have almost 1,200 supporting staff. So we are a little mini city of Europe, accommodating almost 1.5 lakh residential and floating population. And we have almost 57 faculties of education with us. So this lecture that we have designed as a part of NASA celebrations that happen on the 13th, and you are a very important part of that lecture, is nothing but a stepping stone to introducing you to this beautiful city, educational city that we call, and eventually to have these workshops online, offline, as much as possible, so that our students can get global exposure and they can align themselves with respect to the talents and the skill set that is required by other global universities, organizations, and institutes. So I'm sure that children today are super excited for your lecture and your hands-on workshop later on. I am going to be thrilled to see the results. I'm pretty sure, considering that LSAD has always been very enthusiastic in holding these events. I especially like to thank here my faculty who have been very proactive in organizing this and the student bodies who have made this possible. With this, I leave you with Stephen in the morning and Tanesh and Arafat and all our beautiful students. I hope and pray that this becomes a real success and we look forward to more such workshops. I hope whatever deliverables that you get from this are going to set a benchmark for the others, not only in the school, but also in the university, that how well you can do, even in an online class. So all the best to you and welcome, Stephen. Welcome to LPU.
Thank you, Tara ma'am, for a wonderful introduction of LSAD to Stephen. Hi, Stephen. Hello, everyone.
Hi.
I want to introduce Stephen to you guys. He is joining all the way from St. Petersburg, Russia. Stephen is a award-winning architect and a computational designer. He's a co-founder of Kodiia Workspace and SA Lab, where he'll be introducing the portfolio of SA Lab with us today also. And he is building Kodiia, a AI-powered workspace for creative tasks. And as I mentioned, he is a co-founder of SA Lab in the year of 2016, and he has introduced a unique design methodology combining the computational design and digital fabrication. Now he is a lecturer at international programs and he run various workshops over design morphin, digital futures and everywhere. And he is teaching students all the way from like around 20 plus countries, and he has projects published in Arc Daily and like Dizine, major publications of architecture. This is the brief about Stephen. Stephen, welcome to LSAD and welcome to Lovely Professional University. Over to you for the workshop, and thank you for joining us with us today.
Thank you for this wonderful introduction. I'm really happy to be here, and I'm really looking forward to this workshop and the outcomes of the workshop. Well, I think that I will start with a brief introduction to SA Lab project. I will tell what we are doing, how we are doing, what kind of projects are we working on, and what kind of technologies we are using. And later on, we'll dive into Grasshopper and Rhino to talk a bit about cellular automata and generative design. experimenting with rules, and then we will go on with web design basics, understanding how the same logic can be applied to create a web app, for example. This is the plan for the next 2 hours, I guess. Okay, I need to launch one thing here, first of all. Okay. And okay, so let me share my screen. Hopefully you can see my screen now.
Yes, Stephen, it's visible.
Okay, great. So basically, we are an architectural laboratory. We take a lot of time experimenting with different technologies and seeing how we can apply it in the practice. And we mostly started focusing on the architectural projects that are in the physical world, that can be built, you can go into, walk around, and so on. This project is a small showroom, an interior project that we were working, I guess, maybe 4 years ago. It is designed with these parametric structures. Mostly they are made of aluminum, and they are really thin, just like 1 millimeter thin. And we used, of course, Rhino and Grasshopper to design those parametric structures, and a lot of digital fabrication. We had, I don't know why images are blurry, but perhaps I will load a bit later. We had like a lot of form finding process going here. So we started with some simple shapes and then started experimenting, trying to develop a structure that would divide the space of the showroom while at the same time preserve its continuity, creating a one space, yet divided into different functional zones. That's why we were experimenting with those structures here. And first we had an option with like 10,000 pieces, but then using Rhino and Grasshopper, we managed to reassemble it using 485 pieces, which is a lot less than 10,000. And of course, it takes less time to assemble, to produce, and to build such a structure. This thing that you see here in the image on the right, it was built, assembled on site in just 1 week, I guess. And altogether, I guess it took about 3 to 4 weeks to produce drawings, to laser cut all the pieces from aluminum, and then assemble it on site. This is how basically the cutting process and the drawings for the laser machines look like. It's just flat sheets of aluminum with some details on them. And later on, when everything is assembled on site, those flat pieces are beginning to take 3D curved shape and take their final form, and they are grouped into modules, and then those modules are assembled together in a single structure. More images of the showroom. Okay, so that was before 2020, but in 2020, when the COVID happened, we were about to design a few pavilions for a science festival happening in Moscow and then moving to St. Petersburg. We were supposed to create stage pavilions for this festival. and they were supposed to first be assembled in Moscow and then transported to St. Petersburg. But then COVID happened, and the festival that was supposed to happen offline had to move online. And we ended up creating virtual spaces for the festival. We created 2 virtual spaces using the Solar Automata algorithm that we are going to discuss today further on. And those spaces were used to walk around by the visitors. Let me just, so you can walk around, explore the space. You can climb on top of the tower. There are elevators and various steps and so on that you can take to climb on top. And okay, let me turn on the sound. Okay, and basically there are various how would you say this, artifacts or hints located inside the pavilion structure. Basically, there are numbers and letters, and visitors traveling in this virtual space and exploring this pavilion, they were kind of collecting those numbers and letters and then assembling either a single number or a word out of letters to win prizes from the organizers of the festival. So altogether, in maybe 3 or 4 days that the festival took place, about 10,000 people visited those virtual spaces. And this is the project when we started thinking about the alternative possibilities that virtual space can provide to architects, and what kind of architecture we can create virtually, because basically working on these pavilions, we were not facing any gravity restrictions, for example, any budget restrictions on construction. We were just simply exploring the possibilities of the virtual architecture and trying to find the best way to make interactive and fun experience for the visitors. So both pavilions are using Solar Automata, as I said. One of them is growing up, the pink one, and the blue one is growing down. So to explore this pavilion, you have to go below the ground level in this virtual space. These spaces are still working. You can visit our website, find the Geek Pavilions project, or maybe I will share the links later on, and just explore the spaces. Here, this project is built using Rhino and Grasshopper to generate the structures and to fine-tune them to make them walkable and fun to explore. And later on, this whole geometry was imported to Unity. And in Unity, we created this walkable experience, setting up the cameras, setting up the character movements, and so on, collisions with geometry. Later on, it was exported from Unity as a web project and uploaded on the online platform of the festival for visitors to explore the space. And then we just re-uploaded this project to our website. And this was kind of complex pipeline and complex workflow, because first of all, you design the geometry, then you export it, import it into various platforms, experimenting with it. And it takes some time to practice, and it's kind of long process to go. So after we completed this project, we started thinking about how we can create our own web experiences without using game engines, for example, like Unity, because when you export your Unity project into a web project, you get a lot of extra files created by Unity that maybe you do not really need in your project, but because everything is made on a game engine and then exported into a web format, you get some kind of extra files in your final project bundle. So we started experimenting with just simple web technologies using HTML, CSS, JavaScript, and a library called 3JS. And we'll talk about this later on in our workshop as well. We were invited like a year ago, probably, last year, to take part in the first Metaverse Architecture Biennale. And we kind of continued developing virtual projects in our laboratory, in our architectural studio. So this is another example of such a project that's called Fragile Pavilion. And the idea of the pavilion is like it's a repository of sounds, memories, and knowledge that is essential to take with us from the past to make the future happen. So before working on this pavilion, we conducted a few researches asking people different kind of questions. Like, for example, what kind of a sound, if you could just like imagine everything, every sound is disappearing from the world. You cannot hear anything. What single sound would you leave, would you take into the future? And other questions were like, what kind of important event happened to you in the past that formed you as a person that you would not want to miss in the future? So some kind of important event that you would definitely need in the future because it made you who you are. And there were more questions like this. They were, I guess, provoking reflections, provoking some thought experiments for users as well. And then we kind of combined those answers into a structure like this. And this pavilion was hosted on two platforms online. One is called Worlds, and the other one is Decentraland. I think you have heard about Decentraland, and hopefully about Worlds too. And we were creating like two versions of this pavilion because of the technical requirements of the platforms. Like Decentraland requires a geometry with less polygons, less vertices, and so on. And Worlds can give you more space comparing to Decentraland technical requirements. So basically, we were creating like a low poly version for Decentraland and high poly version of the pavilion for the Worlds. With bigger size and more smooth geometry and so on. And let me just walk around a bit. So basically, I'm stuck. No. Yeah, I can walk. Okay. So you can navigate around the pavilion, and yes, you can walk on water here. When you go to this kind of flower-like structure that is floating in the air, you just follow those white particles on the water and on the ground. You can hear some signs here. You can see some signs here, and when you click, you can read the answers that our users were providing for the different questions that we were asking them. And you can hear, for example, this is the description of the perfect Sunday, for example. The soft glow illuminates the room and my purring cat. The phone sits peacefully awaiting the start of the new day. So basically, just some ideas on the perfect weekend for the user, and you can explore more things here. And there is also a special soundtrack created based on the answers that we received. So sometime you can hear a cat sound. For example, sometimes you just hear some rain noises and so on. I guess I can share the link also so that you could explore and check the space. Okay, so maybe there is another project I could show you, just a project that we did for a competition last year, and we took first place in this competition specifically for using AI in our design process. So this project is called Pixport Legos, and there is a company named Pix Moving, and the company is producing autonomous, not buses, but basically they are creating like the base part of the bus, the four-wheel and the platform. And it's all controlled by the AI system that they are developing. And you can, on top of the platform, you can put any function you want. You can make it a bus, you can make it a shop, you can make it an office, a meeting room, a hotel room, anything. And the company is experimenting with the idea of a city that is not composed of buildings, but instead of those moving shuttles, moving vehicles with various functions, and basically the city may be reassembled when different functions, different vehicles with different functions combine and join each other in various parts of the city, for example. So we were not having, we didn't have any specific idea when we started working on the project. And we started communicating with large language models and image generation models, text-to-image models, just trying to describe what kind of a city we want to build and trying to get an image maybe of a city that we want to build. And later on, we got like some descriptions of the city, some sketches of the city, and we started to develop our vision based on those sketches and ideas that we got from large language models and image generation models, combine it with our own visions and our own ideas, and we ended up with a structure like this. It is a modular structure that is composed of 6 types of various modules, and basically the moving cars are going inside and outside of that structure. And the whole structure is transformable, so you can add modules, you can delete modules if you don't need them, and the walls are transformable, so they are made of TFE cushions, inflatable, and you can move parts of the walls up and down, so they are foldable. So the whole structure is really adaptive and can change depending on the needs that you have. We also combined this structure with the ideas of a transport hub, so that you not only have vehicles moving on the ground, but you also have some vehicles that can float and connect with other parts of the city via rivers or lakes, for example, and also a cable system where vehicles can get into a cable capsule and move to another part of the city. So we started with some kind of movements here, trying to transform it into more modular shapes, experimenting with how different kind of modules could combine together, what kind of shapes we could get. And all those schemes and schemes for the projects were made using Grasshopper and Rhino, just some screenshots that were then combined in a single image using Photoshop or any other image editing software. So basically, this is the project. That's how it looks. As a test site for this project, we took a Lagos city in Nigeria, and there is a great market area, and we were thinking maybe we could reimagine the market using those autonomous vehicles and AI control city environment. So we start thinking about how we can reimagine the economy of the market, how we can create cafes, shops, maybe some kind of co-working spaces, offices, laboratories that recycle different packaging, for example, that you have on the market, or different food that is left and is not sold on the market into something else. And we kind of combined this whole all ideas into an economic structure for this new market vision. And then we also had an idea that we could create an app to navigate through this area, to come up with suggestions what people can do in this area, and so on. So these images are just some sketches that we got from AI of some kind of inflatable structures that we were then developing in our project. Okay. I'd also like to say that if you have any questions, you're free to ask them, maybe in chat or maybe some other ways, so that it's not only me talking, but also some kind of a dialogue from both sides.
Yes, Stephen. The thing is, we are running in a webinar streamline right now, so the audience will not be visible
Okay.
to you. Anyways, the students can ask questions on the Q&A box. The Q&A box is open for all the students as well as the panelists. So I request all the students to put up your questions here one by one, and then meanwhile we can come up with the answers. Yeah, that would be nice.
Okay, thank you. I guess that's it with the brief introduction. So if you have any questions, feel free to use the Q&A box, and I will come back to them later. And so our next goal is using Rhino and Grasshopper, trying to experiment with solar automata and see what kind of structures we can generate and how we can control them. Okay, so I got a simple script prepared here for the workshop. I wonder if I can share the Grasshopper file with the students. Is it possible?
Yes, sir, it's possible. People are already using Rhino platform, but Grasshopper is something new to them. So yeah, the script would be beneficial.
Okay, so how do I share it? In a Q&A? Or
Or you
in
can mail. Is it possible to mail or?
I can I use chat, for example?
Yeah, try sending. I don't know if the document will be able to say share here.
Okay. 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 So seems like I sent a file.
Yes. Yeah, I got it. All right, I'll share them on the class WhatsApp group.
Okay, thank you. So this is Rhino and this is Grasshopper. Grasshopper basically is an extra feature for Rhino. Long time ago, it was like a separate program that you had to install to use it along with Rhino, but nowadays it's all integrated into Rhino interface, and to launch Grasshopper, you just need to use this round green button on your standard panel in Rhino. And what is Grasshopper? It is a visual scripting language. It's kind of a programming language, but it's made with those gray rectangles, boxes. They are called nodes, I guess. And each node is just like a simple command that is executed by your computer. It has some inputs that you can that are necessary to control the execution of the command, for example, and it has some outputs providing the results of these command executions.
Yeah,
So
just a moment, Stephen.
okay.
Students, please check your WhatsApp. In the group, I have shared the CA asset file. It's a Grasshopper file. Now, what you guys will do is open the Rhino and then type in Grasshopper, enter. There will be the Grasshopper portal for you visible, and then go to file and then open this document that you will download from the WhatsApp group. I think that should be easy for them to cope up. Yes, Stephen, sorry, sorry to disturb you. You can start. Yeah.
Okay. So all the nodes in this file are native and they're available in the standard Grasshopper window, except for two. The first one is called loop start, and the second special node is called loop end. And those nodes are provided by a plugin named Anemone. And if you don't have this plugin yet, you can go to foodforrhino.com and search for Anemone, and here it is. So it was not updated, I guess, long ago, and what you can see here, the last version is 2015, but it's still working. And the idea behind this plugin is that it helps you create loops. So some kind of some pieces of code that are repeated over and over, depending on how much times you want to repeat this kind of code. I guess there are other plugins providing the same functionality as Anemone, maybe Hoopsnake or something like that. But for this definition, I used Anemone. And let's try to understand what is cellular automata and how we can implement this algorithm. So basically, cellular automata is kind of a mathematical model that was invented in 1940s by two scientists from the United States. They were working on the idea of robots and kind of machines that could reproduce themselves. So they were trying to find a mathematical description of this kind of a process when a machine can rebuild itself, repeat itself, and they that's how they ended up inventing this cellular automata thing. So in classic case, it is a 2D grid, two-dimensional grid. So for example, I have a grid like 4 by 4, but usually it's more. And I have cells in this grid. And for example, here is the cell that I'm looking at. And this cell should be familiar with what's going on. And it depends on usually on how many neighbors are alive or dead. So for example, if I'm looking at this cell, and for example, this cell is dead here, and this cell is dead here, and maybe this cell is also dead. So for every cell in my grid, I will calculate the number of alive members. So this one is alive here, this one is alive here, this one is alive here, this one, and this one. So I have like 5 neighbors alive and 3 neighbors dead. And then I can have some rules that maybe if the cell has 2 or 4 neighbors alive, it will be alive on the next generation, or some other rules I can come up with. And these different rules produce different results and different geometry and structures that you can simulate. So basically experimenting with the rules gives you ability to generate different forms and different structures. One of the most famous examples of cellular automata is called Game of Life. And it is a computer game that was created by John Conway in 1970s. It is a strange computer game because it is not meant to be a multiplayer computer game, or you don't have any mission here. You just set up like basic starting conditions for the grid, and then you click the start, for example, and the rules of this cellular automata are applied to the starting conditions generation after generation, and in each generation new state of each cell is created based on the amount of neighbors and the rules provided by the automaton, and you can see something happening on your screen. And depending on your starting condition, you can get different results. And basically, there are a lot of experiments available online with cellular automata. People are creating computers using this simple logic. People are creating, I don't know, clocks, some kind of simulations, various examples, and a lot of different projects are creating using these simple techniques. So the idea of the algorithm is really simple. You have a cell, you calculate the amount of neighbors with a certain state around this cell, and then you decide what should happen to this cell based on the data that you calculated. And these algorithms are used in biology, for example, to simulate the growth of plants spreading of forest fire, for example, or a virus. It is also used in physics to simulate smoke dynamics or fluids or gases, and it can also be used in architecture to generate some city environment or a pavilion or some kind of other architectural project. And with the original Game of Life, you can see that there are some cases when cells are starting to kind of move around, and there are different figures that start to move in space, and then they collide and create different shapes, and like this one. They have different names. For example, the moving cells are called gliders. They like this one here, for example. This thing is called glider because it glides somewhere. But with time, mostly this system will come to a stable state composed of various structures like this, the one that you see here, that are not changed with time. They become static, even though we recalculate the cell states generation after generation. So in our Grasshopper file, let me just disable all I have and see what we have at the beginning. So the first thing we create is a grid, and this is created with the square grid component. It creates a grid of rectangular cells. Each cell is 1 by 1 size, and we have 10 cells by X direction, 10 cells by Y direction, and we want to make it all 3D. So we're gonna experiment with the same logic that I just described, but implement it in a 3D grid. So the next thing we need to do is to grab the centers, for example, of our cells and move it up like this to create a 3D grid structure. How do we do this? We grab our centers, we grab the move component, we have the direction of the movement. It's a z-axis, so we use unit z vector. And then we need to provide the amount of times that we want to move our initial points in the z direction. And to provide this, we use series component. And for count value here, for count input here, we use the same number of cells that we used to create our grid. So it's 10, or maybe you can then change it to whatever you want, like 15, for example, to create a bigger structure. It depends on the hardware that you use. The more advanced hardware you use, the more cells you can generate, the more complex structure you can create. So basically, I start with 10 because it is a simple and easy to simulate thing, and you can just understand how it all works before building something complex. So if you're working with Grasshopper for the first time, you may also be wondering what kind of wires are these wires? What is that? Some wires are depicted with a single line, for example, here, and different type of wires simulate, not simulate, but depict different types of how information is structured and delivered from one node to another node. So for example, here I have a panel node, which is just a simple text node in Grasshopper. And I have a single line wire connection here. This means that in this wire, I have like a single data element being transported from the panel to this node, for example. Here, I have, for example, a double wired connection. This means that here I have a lot of different a lot of different numbers or different data elements. And here I have like 10 numbers. So here I have just one number and the wire is single line. Here I have 10 numbers and it's double wire. And here I have dashed wire, dashed connection. And this means that I have different lists with different amount of data inside. So for example, if I plug in a panel, I can see what's going on inside. I see different lists like this one, 0, 0, 0, and the next one is 0, 0, 1. And in every list is some kind of data. For example, here is a rectangle depicting the grid cell. And you can think of lists in Grasshopper as boxes, for example, and you can have different items, a different amount of items in different boxes. There are different commands to transform and operate lists or data trees. It's also another way to call them. And the most used commands are flatten, that combine all the data items in a single box, or graft. Graft command takes all the data items and put every data item in a separate box, for example, in a separate list. And we need this graft thing here, graft command here on the input in our move geometry node to create this 3D grid. If we don't use graft here, for example, you will end up with something like this. And if you use graft, you'll end up with a normal 3D grid that you want for our algorithm here. So the next thing we're going to implement here is the random initial states. How do we do this? We just use a random component here. We calculate the amount of points that we have in our grid. We generate random integers, either 0 or 1, to generate random initial states for our cells. And if we just see what happens here using the call pattern node, you'll see that we have something like this. So like this. So we have our cells, but then some of them are just randomly removed. And we only have cells that have the random 1 state, and those that have random 0 state are removed from the visualization in our Rhino screen. But we need to record 0 states as well. We are not just removing the cells, we just provide them with different cells, different states. and we need to record all the states for us to be able to operate on them later. So, okay, let me just move those notes a bit. And get some space. Okay, let's see what happens in our loop. So our initial structure, our initial states, and our points, they are all provided as input for our loop start node here. And we have also the amount of generations we want to create. You can control it with this panel. Instead of 3, you can type in 10, for example, and then the generation will continue 10 times. And you have a button to trigger it all from the beginning. You can control the seed value here in your random node to change the starting positions. And then what we do, for each generation, we get the number of points, we get the states for every point. We calculate the number of neighbors for each cell that are alive and have like 1, for example, state, yeah. And then we kind of calculate it all. So we get the closest points to our point that we're looking at. We just control the number of points that we are calculating using the distance. And if we have a cell which is 1 by 1 by 1, you want to use the distance which is 1.5 approximately. You just then calculate the total amount of neighbors that are alive, and then you have 2 nodes that help you to define the rules. So here we are saying that if we have amount of neighbors either more than 2 or less than 8, so for example, it can be 3, 4, 5, 6, 7, and maybe 2 and 8 also, yeah, and 2 and 8 as well, then this cell is alive in the next generation. And we kind of record this cell in our list of states and list of cells, and provide it all into the loop and data. And then we just get the last generation from here, from our loop end. So our last generation's points, last generation states for the points, just again remove those that have 0 states. And later on, we can visualize it all using a box, for example. We can create a box around every point here. Okay, and it will look something like this. And the last part of this algorithm is just to make it more clear in the sense of geometry. So if we just create a lot of boxes, we have a lot of polygons and box faces that are not visible to us, but still generated by our algorithm. So with this group of nodes, we just remove those that are not visible to us. So you will see that there are no hidden box faces inside. So it's just like a single surface around those points. And we also transform it into a mesh just to make it more easier to render. And we get a structure like this. So I can retrigger my calculation, and depending on the amount of generations, I get a different structure. I can come up with different rules. So for example, if I have only 2 and 4 neighbors, I will get a more porous shape, for example. And if I use more neighbors here, like, I don't know, 2.9 or maybe 3.9 or 3 and 9, I will get more more unified shape. Basically, you just, if you set up 1 and 9, for example, you can get even something close to box-like structure. And so experimenting with the rules, experimenting with the generations, you can create various kind of structures. And you can also introduce some extra logic here in our loop, or maybe some extra logic here with the final points. So maybe you don't want some points to be generated in a certain area. So you can add an attractor point somewhere. You can maybe calculate a distance between those points and geometry, and you want to pick a distance, for example, that is smaller than a certain value. Maybe 5 is fine, or maybe 3 is fine here as well. So you can just get rid of some tiles that are not okay. 3, 12, 13. Okay. 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 So here I took only the cells that are close to the attractor point, or maybe I can just grab only the cells that are far away from this attractor point, and that's how you can further control the geometry that you create. So for example, you're using those cellular automata thing in a city environment, and you have some buildings that are located nearby, so you want to have some distance from those buildings, and that's how you can control your outputs using the attractor idea in your algorithm. Okay, and that's it. That's a simple idea that we are using in Grasshopper. So I hope everything is fine. And if you have any questions, feel free to reach out. Do we need to make a break, or we can continue with our next phase of the workshop? Okay, so there is no need for break. Then let's continue to web design and web design basics. If you have any questions after the workshop, feel free to reach out. I hope I will be able to answer them and maybe provide some solutions. Okay, thanks. Let's continue. So our next step is web design. And for that, I suggest using this Kodiia platform. Kodiia is a platform that we started developing in SA Lab during the COVID times, because we were hosting workshops, experimenting with web technologies, creating virtual structures and virtual spaces, and we just couldn't find the platform that suited our needs. That platforms we were using either were specifically designed to build things or either specifically designed to teach coding, for example. And we kind of wanted to create a mix, some kind of a mix platform that provides tutorials with step-by-step instructions and some coding possibilities. So if you go to kodiia.com, okay, take a break for 5 minutes. Okay, then let's take a break for 5 minutes. And see you all in 5
Hello,
minutes.
Stephen.
Yeah.
Hello, Stephen.
Yep.
Yeah, since it's a long lecture, I think we can take a 5 minutes break, and then
Yeah, no worries.
we'll start with the other part. Till then, the students are discovering, going through the Rhino file, and they're checking the things that you have just shown us.
Okay.
Yeah, so we can continue in 5 minutes then.
Okay.
Yeah.
Okay, so are we ready to continue?
Yes, Stephen. Welcome back. We can start now.
Okay, so I have a question in the Q&A section here. How is it determined which pattern that we get from Grasshopper is suitable and should be designed upon? I've typed my answer here, but I'd like to talk about it also. It depends on what kind of building or structure you're generating using the Grasshopper algorithm. So if you're working on an office building or a residential building, for example, you will have certain requirements towards your geometry and certain restrictions that should be implemented towards your design. And if you're designing a pavilion, for example, you will have another requirement and other restrictions. So basically, it all depends on what are you designing. And I would say that this whole algorithm and this whole approach is not something that will give you a final solution for your design. I would say that this is kind of an experimental research stage when you're just iterating through forms and geometries and see what works, see what's not working. And maybe you can build some initial ideas in this conceptual stage and conceptual research and develop those ideas further on. I guess that you will be experimenting with AI models further on today in the workshop, and they are super helpful to visualize, for example, those quick sketches that you can generate with Grasshopper definition, and to imagine how it can look not as a wide set of boxes, but as real buildings with real materials and so on. So I would say that what we are doing is an experimental stage where you're just exploring different kind of forms and form ideas that you can then further on implement in your project. And what are those ideas that you will pick and develop later on? It depends on you and your vision of the project you're working on and the requirements to the project that you're working on. So the platform that we're having here is called Kodiia, and it's available on kodiia.com. If you go to that platform, you just can press Get Started button, and you will be provided with this kind of a starting template section. What we are looking into today is the template called CA Craft. Solar Automata Craft, like craft is from something like Minecraft. If you're logging on this platform, you'll be able to create a project. Let me just log in and yeah, so you'll be able to create a project. Just choose a template. If you don't want to register, it's not a problem. You can open Sandbox. Let me first open a Sandbox. The Sandbox will provide you with all the files and all the code necessary. And you'll be able to run it and change the code and experiment with it, but you will not be able to save your project. And if you create a project, it will take some time, but you'll be provided with the ways to save your project in the cloud to rename it. For example, cellular automata generation. You can also upload some assets if you want to use them in your project. And here on the right, you have a panel called resources, and it has a built-in AI system that can answer your coding questions, for example, or design questions. Like you can ask it, how do I generate a building with cellular automata. And in some time, it will provide you an answer. It's a multi-agent AI system. So basically, before answering your question here, multiple LLMs are answering it, and then the final answer is combined and presented to you. So it basically comes up with some design vision. What kind of a project is this? What kind of libraries you can use? What kind of rules you can use for, if we're talking about cellular automata, there are various rule sets explored by scientists and people that were experimenting with these algorithms before. And there is also a high-level code overview and some detailed code split into various sections, for example, HTML or CSS, and then JavaScript as well. This thing is using P5.js library here, and we are going to use a 3D library using Three.js. So basically, every web project that you're working on consists of 3 parts. The first part is called HTML. It is short for Hypertext Markup Language, and it was invented in 1989 by a person called Tim Berners-Lee. He was a scientist, and he came up with an idea of using hyperlinks to connect different documents on different computers. So instead of going to another computer and opening a different document, you can just create a link in your own document on your own computer. And by clicking this link, you will be presented with the document from another computer. That's how HTML started. Then a few years later, it started actively developing, and it came to a condition where multiple styles should be implemented to the documents of HTML. People were thinking about how do we change colors of the text that we are using and so on. And that's how CSS appeared. So basically, if HTML is about what we're seeing on our web page, then CSS is about how it looks like. CSS is short for Cascade Style Sheets. So it's a language to describe the font colors, fonts used on your web page, how your web page is composed, either you're using a grid layout or some other options available, what kind of shadows you're using to various elements and so on. So basically CSS is about styling. And then in 1995, a new programming language was presented to make web experiences interactive. And this language was first called ECMAScript, and then it was renamed to JavaScript. just because at the moment Java language was super popular and they wanted to kind of create some kind of similar popular language. So they named it JavaScript, similar to Java language, but those are different programming languages. And JavaScript is responsible for the interactivity on your web project. So if you go to index.html file, you can open any file and then click run. And after maybe some time, you will see a white background. First, you'll see a white UI here on the top, and then a white background. Because it takes some time to upload the 3JS library that we're going to use to generate the 3D structure here. So if you're looking at HTML file, you should be seeing basic structure of your file. First of all, it says that this is an HTML file in the first line of code, doctype HTML, just a line to tell the browser that this is an HTML language that you're looking at. Then we have HTML tags. HTML as a language consists of tags. Tags are maybe like commands. You can think about it as Lego blocks, for example. Those are the blocks with pieces of information that you combine together to create your web project. So every HTML file is divided in two parts. First part is called head, and it is located between the two head tags. Tags are tags come in pairs usually, but not always. So head tag has the opening tag and then the closes tag with slash before the head word. And this part of HTML document is responsible for different kind of technical information that you may not be seeing in your web page, but it is definitely used by your project. So you upload some libraries here, like 3JS, for example, using those script tags. You upload some styles, like this line with link tag here. You create the title of your project that usually you see on the tabs in your browser. So those inscriptions on the tabs in your browser are coming from this title tag in HTML document located
sorry
in the
to interrupt,
head.
Stephen.
Yep.
We have a question here
Okay.
from Lucky. Lucky has raised his hand. Lucky, please put up your question in the question answer session, or you can speak here. And everybody, please put up your questions in the Q&A session so that it's easier to answer one by one. Yeah, okay, Stephen, you can start. Sorry.
Yeah, okay, no worries. The second part of HTML document is called body, and it is described with two body tags. Again, the first one is the opening tag, and the second one is the closing tag with the slash before the body word. And this is the part that presents everything that you see on your web page, that you actually see. So, for example, here we have some headings, like with this H2 tag named C, saying C aircraft. And if you change this to something like to anything, you will basically see that this changed in your web project as well. So there are different tags in HTML for different type of information and commands. headings to generate headings on your web page. They are presented with H tags and followed by a number like H1, H2, H3, 4, 5, or 6. And then there are different kind of inputs. For example, here we're using inputs to set up the neighbors amount in our algorithm. There are buttons to create buttons, like we have a tag button with the inscription generate, and we have the same button on our web page. And then we have this export button to export an OBJ file from our web page. And then we have a canvas tag here, all everything that is connected to graphics in web design, every graphic app, anything that you see on a web page representing graphics, interactive, I mean graphics, is located usually in a canvas tag. So it may be a game, for example, or an interactive visualization or something else. There are special tags for images, for videos, for audio, for example. But if you want to create some interactive graphics, then you need to use canvas tag. So basically, this is just the structure of our web page. Then we have this CSS file here. And CSS is for styling, as I said. So what we have here, first of all, we import a font. If you want to use some specific font, there is a thing called Google Fonts, fonts.google.com, and there are various fonts available here. And you can just search for them or search for some kind of keywords. So for this project, I was looking for a pixel-like font. And here I have like Pixelify Sans, for example. So you click on the font, and then you have this blue button, Get Font. And then you have this button, Get Embed Code, and you're provided with various options on how to use this font in your project. For the web project, we are using the import option here. So here we have our line of code, import URL, and then this font that we are looking at in our project. Where is it? Here is it. Yeah, so if you want to use any other special font, you can use this platform as well. And this is how you import some special fonts to your platform. You can also specify some fonts that are usually available in every operation system, like Arial, for example, or Times New Roman, and so on. And if HTML consists of tags with those arrow-like brackets, then CSS has a different syntaxes, and you can see a lot of curly brackets here. And to style an element in CSS, you have to specify the name of the element from HTML. And then between those curly brackets, you specify the properties for this element. So for example, here we have body element, and we specify some like fonts properties. Sans serif means that you don't
Yes,
have
Stephen.
those. Yep.
Yeah, Stephen, thing is, we have been getting some queries here. Like students are getting confused between these HTML files because there are lots of things that you're showing in a go. So it's
Okay.
it's warming to know all these. It would be better if you could do something and show us so that we could understand what particular HTML file is used for to generate what. Like it visually, if people see that, they could grasp it better.
Okay. So HTML is for your basic structure of your web page. So as I was talking, we have a heading option, for example, here, heading tag, and with an inscription. It says CA generation, and we can see CA generation here, for example. So if you change this inscription, it will also change on your web page. Just don't forget to click run again. So here I type CA design, and this is CA design that we have here. That's it. So basically, HTML is to provide necessary elements on your web page. Then CSS is to apply styles like fonts, colors, and so on. And then JavaScript is to provide some interactivity, like this generate button to generate various structures, or this export OBJ button that will save an OBJ file to your computer with this geometry that you generated here. And I was just describing how it all works. It is not necessary for you to grasp all this to be able to work with this app. It's just a simple explanation how things work here in web design. That's it. Let's take a look at the JavaScript file. And it has a lot of code here, but basically what it does, it recreates the same algorithm that we have in Grasshopper using the JavaScript and 3JS library. So what is 3JS library? Let me go to 3js.org. This is a library that allows you to create virtual 3D experiences that work in the browser on any device. You can take a look at various examples here, how people are using it, and what kind of projects they create. I usually show this one. There is a car brand that creates an electric vehicles. It's called Faraday Future, if I'm not mistaken, and they are using 3JS just to display their car. And using the arrows on your keyboard, you can control the movement of the car. So it's a kind of an interactive experience that presents you with the geometry of the car, the model of the car, and lets you, drive around using your web browser. That's it. And also there is a great documentation for this library on how to create scenes, how to implement various stuff. And there is also an example section here showing you various projects. And then there is available source code here, so you can take a look at how this project was created. So this is basically a scene created in some 3D editor like Blender, for example, with animated parts. And then this geometry is uploaded to a web project, and 3JS is used to display it and to play the animation. So all the modeling is made somewhere else. 3JS is not responsible for modeling. It is basically responsible for visualizing the 3D content in the web browser. And then there are a lot of other examples. You can make an ASCII art, for example.
Stephen, sorry for disturbing.
Yep.
The workshop looks great. Can we streamline in a way where you will be showing a student to how to make a model and the student parallelly doing the model? Can we streamline in this way? So that people get a more better understanding and they'll be making some forms and exploring forms.
Yep, no worries.
Okay, no worries.
So in your web app, you have like generate button that when you click this button, you get a shape and a structure, something like that. You have an export button to save this form on your computer. And you have this minimal neighbors and maximum neighbors options here, the same as we had in Grasshopper definition. You can just set up various amounts and see where it goes. So for example, if I say maximum neighbors to 8, nothing will work because all the cells will disappear. It's not a problem. Just type in some other number and see where it goes. If we have minimal neighbors to 4, for example, we get some block-like structures. If we have even less numbers, you come up with various shapes. Well, you can treat it in various ways. For example, you may say that this is a kind of a facade and then some windows or openings in the facades. Depends on what kind of project you are creating. So for example, if I have like 3 and 6 neighbors, here I have a more porous shape with less voxels and not so box-like outlines.
Stephen, Stephen, could we have this link shared to the chat box? Because people are finding
Yes.
it difficulty in turning on this, searching this. It would be better if we share the URL.
Okay. Let me do it once again. So here is our homepage. I can share it here, for example. You need this CACraft template here, and then click, for example, Open Sandbox. And here is a link for the sandbox. Okay, and in Sandbox, you just open any file and hit Run. And then hit Generate, and you're ready to go to explore the shapes and see how it all works. I don't know, should I go in details on Three.js and how this code works here? Will it be too much of new information for today?
I think it's a lot of information, but what we're planning is 2 to 5. We want students to work on one particular form where they can generate a form and then they can give up a submission as a as a part of this workshop as an assignment, and the others things they could just go through what they can they can explore the part. Is there any particular task that you can share with the students that students can do it and show you?
I think that if they come up with some 3D forms that they are excited with, that will be enough. I don't think.
Yeah, so once the form is done, people can generate it and then they can export it, right? Export it to .obj. And after that, we can open this .obj in Rhino.
Yeah, let's try and do this. So I hit export.
Yeah, and then it would be nice even if you show us some AI tools where they can render it and come up with some ideas. It could be a basic idea board with this geometry. They can give it a activity.
As for AI tools, I don't have any special AI tools prepared right now that you can just drag and drop your shape to. I can share the project that I was sharing on LinkedIn with you as well. Just a second. Okay. So here is not here, not here, not here. Okay. So new tab, go to new tab. 3D editor. Okay. And here is this thing. Okay. And this. So this is the kind of experimental project that we've been working on lately. It basically provides the same idea with generating something with Solr automata algorithm that we're discussing today. And it has some extra feature here. So on the right, you have a panel where you can provide a prompt. What kind of 3D model is this? And then click the visualize button, and it will generate an image. It may take maybe 30, 40 seconds, maybe a minute to do this. But it's still in the beta and testing stage. So here is the image that it generated. So basically it took an composition from this 3D canvas with the Solr automata generated structure and combined it with a prompt written here. And the final result is an image like that. So feel free to experiment with it, but it may be buggy and not so polished. Again, other AI tools that are usually used for this kind of projects here are maybe ComfyUI. Yes, this is like a node-based editor that lets you work with AI models and generate various images, implementing the same pipeline that we have here. Take one image and then add some prompts, styling, and so on, and get another image. I'm not sure if there is a web version. Okay, so there is maybe a service named ComfyUI that is available on the web. Maybe you can explore it. I've never tried it before, but I don't know. This will work for you. Okay. So I guess that this is everything I could tell you today. We're not going in depth into 3DS and all this coding crazy stuff here. And then what else would you like me to cover? Is there any questions?
Hi, Stephen. The 3D forms looks wonderful. Like, I want to know, like, what is the minimum, maximum neighbors we can go? Like, for suppose, can we go like 40, 50?
No, you cannot. Just imagine like this. This is a grid structure.
Okay.
Yeah, and so the minimum amount of neighbors is 0, for example, and the maximum amount is it's a 3D grid structure. So you have 9 neighbors, but in 3 layers. So it's 27 neighbors. And if you remove the cell that you're counting, it's 26. So I guess if you put in 26 or maybe in 27, doesn't matter, and click generate, you'll get just a simple cube.
Okay,
So
so we are
this,
making voids in a 3D.
yeah. So basically it means that every cell that has at least 2 neighbors alive, or some neighbors between 2 and 26, it will be alive. So it all comes up as a cube. And if you put some values between 0 and 26, you will come up with some Perl structure. And the more the distance between the minimal neighbors and the maximum neighbors, the more I think box-like structure will be. So if we say 1015, it will not work. If we say 315, it produces, and sometimes it produces some voids inside. So it may be also an option to explore what's happening inside of this shape, just to get some kind of maybe an interior idea or something like that. So we are not required to just look from the outside and at this form. Sometimes beautiful things happen inside, and you may also explore what's happening inside.
Stephen, is there any way we can change, like, for suppose, let us say my students wants to explore different forms apart from maximum 26. Is there any possibility they can try that out?
Sorry?
Like, are students allowed to create any structure out of this? Like, they want to create a different form. Is it possible?
A different form, you mean not a box-like thing?
Yeah. It's like a huge, for suppose, let us say they want to create a 10 floors of different form. Is it possible with this?
It is possible in Grasshopper, for
Okay.
example. You can grab the points that you have here,
Okay.
and then maybe you have like a sphere, and you can like create a sphere in every point, and you'll get a different shape as well. Even more, you can create your own geometry, any kind, but then move this geometry to the points. So you kind of create an asset and then move this asset to the point's location and reassemble this structure, not of boxes, but of your assets. And you can also make some smooth forms. For example, if you join this mesh into a single object and then use something like Weaverbird. I think I don't have Weaverbird here. But I have this smooth mesh here. Just I need more. Things happening here. Okay, using different plugins, you can modify this form. Okay, so this smooth thing is not working here. Mesh join, build vertices. Yeah, okay, this thing works. So here, for example, you can smooth your mesh and make it not so box-like. And the idea that I was talking before is, for example, if you have, I don't know, anything modeled in Rhino, like, for example, let it be a cylinder shape, just as a quick example, you can grab just let's move the shape to the start of the coordinates. Grab it in a grasshopper. There is a geometry node, for example. Set this shape here and create a vector from the starting point. Let it be start of the coordinates, then to your points that are generated by cellular automata, and then use this move node just to move your geometry to every point. And here you have your cylindrical shapes implemented to the points locations. And
with the particular script, can you show us, like, my students wants to explore, can we create any skyscraper type with this type of script? With this particular script, can we explore any high-rise structure type if possible?
Yes, of course. You can control it with those initial conditions. So here we have a grid which is 10 by 10 by 10 stories high, but you can create like 30, for example, stories high. Just let me remove this thing. Okay, mesh plane, enable. Just fixing the rendering back again. Okay, so if we want something like a skyscraper, just plugging your count thing, and here you are having a vertical structure. We still have our attractor here that removes some points in the bottom of the structure. Okay, so there you go.
Can you share us this particular script with the students, like the updated script, if
Yep,
possible?
no worries.
Stephen, there's a problem that we see that we need to download the plugin Animono that you have told us before earlier, right? Now, what we face issue is that it's downloading and working only in Rhino 4 and 5, not in 6 and 7.
I'm using Rhino 7 and it's still working.
Okay, really? Okay.
Yep.
So a few of the query was this that it's not supporting or something. All right, we'll check it again. Yeah.
Stephen, no problem. We'll come up with like the technical problems. After sharing the script, just show us how to use that plugin for the students so that they get a basic idea and they'll work after this. So it'll be more helpful.
So, okay. Let me save this as CA rise. And let me share it with the document. Okay, so I shared the updated script.
Yeah, I got it.
Can you say some models or checkpoint for stable diffusion specifically for each category, like model making, render, or concepts? I don't think I can really provide some helpful information here. Basically, in my experience, right now, I'm using just a stable diffusion Excel model with some ControlNet to grab the overall composition. I know that people are creating their own fine-tuned versions using LoRa and some other techniques and their image libraries to train the model more on a specific style, for example, or a specific geometry they want this model to produce. So I wouldn't say that there is a one size fits all solution, like a universal solution for these properties. I would say that you have to use different LoRa's and different model versions for different tasks that you are trying to solve with this.
Okay, Stephen, thank you. Like, can you show us the plugin, like how the plugin works? Just a small intro, that's it.
We have two components from the plugin. The first one is called loop start, and the
Okay,
second one is called loop end.
okay,
So it creates like iterative logic between those two components.
okay,
On the input in our loop start component, we have a number of generations we want to create. So how many times we repeat the code between those two components. We have a button to trigger the generation. We have a point list in our data input. And if you zoom into this component, you can add more inputs. We're using those plus buttons. And the second input we have is our states, like zeros and ones for our points. And here is some logic between those two components, the solar automata logic that calculates the amount of neighbors and then creates a new set of points and a new states for those points, and they are fit into the loop end node, and that's it.
All right, so everything is included in the script. Yeah, we'll explore that. And yes, Stephen, that was amazing shot of works that you have been showing us, and I think it's bombarding their brains. People are having lots of questions and queries. Definitely, it took time for them to digest the fact that this is all are happening outside India. And I think that would be really much wonderful if you comment on their works when they submit today by 5. And definitely we'll be adding all these works to our Instagram. And we would like to have your Instagram ID where we can tag you along, and the students' work will be there, and you can comment on those works if any queries they have. I think that
Okay,
would be nice session.
I will share my Instagram with you on LinkedIn then.
Yes, yes, sure. You can connect it with Chunesh, and we can get it done.
Yep.
Yeah, and we are out of time now. I think automatically this video call will close at 1 in a minute. So thank you again, and thank you folks to join patiently. Yeah.
Good luck with your projects.
Yeah, good luck. Thank you. Thank you, Stephen.
Bye
See you
bye.
again. Bye-bye. All right, students, we'll see you at 2 p.m. All right. At 2 p.m., I want both the sections to be present in the class. I will introduce the task, and we'll discuss again what exactly we are going to do and what we want within 5. Okay. No homework now. You can leave. Thank you.